the second lecture of Gonzalo. So please, Gonzalo, go ahead.
Yeah, thank you, thank you. Hello, great to see you again. So in this second lecture, I want to continue with basic aspects of quantum field theory, which I'm aware most of you know by heart, but I really want to spend some time on them. And I think I will be, if I manage to do it well, I will get to the point where I will introduce what are called quasi-de Sitter spacetimes, which describe inflation, and I will cover basic aspects of what is called single field slow roll inflation. So we're really getting to the point where we will start computing very valuable stuff for inflation, coming from inflation. Okay, so where were we yesterday? Let me remind you, we got to the point where I wrote an action, and we will do this quite often. We will throw actions into the blackboard, and then we will examine the consequences of them. So this is a pre-exercise of this endeavor that we will do doing most of the time. So let me write it again. So we have this integral, and then the action that we wrote had this form. And I was focusing on a specific potential. So I wrote precisely this. Normally we put a factor 1/2 in front. It's just a normalization factor. So this is the example we were examining yesterday. By the way, I just assume as an obvious thing, but this is always wrong to do, that we all agree what is the meaning of this. So I should not assume that, because there is a convention in between, which is about the signature of the metric. But normally in cosmology, very rarely, you don't work with this signature, which is the mostly plus signature. So I was just assuming that. So let me just be more specific that we are working with this convention in Minkowski. Later on, of course, we will do cosmology, and we will introduce the scale factor and so on and so forth. Okay, so this is mostly plus. Okay, and I was assuming that. Yeah. Okay, so let's go back to this. We now vary the action, of course, and we get the following, the minus sign, and we got to this point. So remember, I want to emphasize something which is not always obvious. This is a classical action. We derive a classical equation of motion, but yesterday, I hope you agree with me, we understood that we can trust that this equation is also valid for the field operator that we're really interested in. Yeah. So remember, this is a tool to derive Hamiltonians which evolve relativistic systems. That's the point. Yeah. If you play with what is called the path integral formalism, this reappears, yeah, from the actual Hamiltonian, which is a quantum Hamiltonian. So sometimes you feel like, oh, I reobtained something which is classical out of something quantum. Yeah, but this is a device in the perspective that I'm taking. Okay, so we get to this equation, and now I say, well, I know this equation is satisfied by a quantum field operator. So now I very confidently I just do this, because that's the outcome of last lecture, yeah? That we can do that because of the algebra involved with quantum commutators, yeah? Okay, so now we have to deal with this, this equation, which is valid for a quantum field operator, and now we have to solve it, yeah? So what I wrote yesterday was the following. I just place an ansatz for this. So remember my conventions here, which are opposite to Roman's conventions. And so here, what did I write? I wrote the mode function in such a way. Then, no, let me put these funny operators, b hat, which is function of k, And then I wrote plus a k dot x, good. And then the complex conjugate or the Hermitic conjugate, which I will make it explicit at least once, which will be this guy minus a k dot x. So this is what we got. Yeah, I'm just repeating things that I mentioned yesterday, but I think it's fair to do it. And then you grab this, plug it in the equation of motion, and you will get now that the equation of motion after plugging this here, then the equation of motion for the mode functions, not now I'm not talking about the full field operator, for the mode functions is going to be this, okay? So from here we solve this equation of motion and we got the solution that in general looks in the following way. It's just, let's see if I remember my own conventions. It has, I put a minus sign here, and I think I did, I took the complex conjugate of beta. It's just a convention, it really doesn't matter. So these are just integration constants, and that's the solution. Let me just remember if I did that. Yeah, I did that, okay? So this is the solution. This is the general solution to this equation. Yeah, nothing new. Oh, yeah, I never clarified what was omega, but again, this is just me assuming that this was obvious. Omega is just the square root of k squared plus m squared in this. Okay, so this, of course, is a smoking gun that this is relativistic because this is just, you all know this is just the spectrum of free particles in a relativistic theory, yeah? When k is identified with the momentum, which is true because of de Broglie's principle, yeah? Okay, so good, we have this, and now I'll remind you of another fact that we discussed yesterday, is that this algebra that ensures that the Hamiltonian is relativistic required another rule about quantum commutations, and this is that we need to satisfy with our field the following commutation relation with what we call the momentum. I put a prime here, just because I forgot to put a y. And this is going to be I delta of Dirac delta x minus x prime. So this is the quantum commutation relation that we need to satisfy. There are more. This is not the only one. There are others, which is phi and pi and pi, but those are zero, so I'm only writing the non-vanishing one. So now that's more or less what I managed to say last time. And what I said yesterday is that in order to satisfy that commutation relation with this ansatz, and this was an exercise, which is also in the, did you all get my notes finally, by the way? You downloaded, okay, great. So this was one of the exercises of the note, is to show that after plugging this and demanding those three commutation relations, of which I only wrote one, you get to the following. So the outcome is that there are basically two outcomes. One is that you do need this to hold. That's one condition that you should find if you did work it out. And the other condition relates to, so this is a condition on the integration constants, but we also have these operators, yeah? And so in order to satisfy the quantum commutation relation, you need a condition on the operators, and this condition is the following. Very well known to most of you is that so hat daga k prime. So if we compute the commutation relation between two of these guys, one with non-daga, the other daga, and this is going to be since I have this convention, I will put the 2 pi to the 3, delta 3 of k minus k prime. And then there are more commutators, but the other ones here I'll just be more symbolic. you fill in what is missing. Those are the other two. Okay, so that's where we were left. Okay. Okay, so now I start the real lecture today. Are there any questions about any of this? Is it just very well known? Or any other question about the last lecture? Okay, okay. So let's now move on. Yes, please. I wrote those. Well, after what I said yesterday, now I want to describe some relativistic system. Yeah. Of course, if I know the system that I want to describe, I will guess what is the action that is describing the degrees of freedom of that system. Yeah, that's called modeling. I have to model the. Here I'm just saying, well, I'm totally ignorant about anything. I will just try the simplest action possible, and let's learn what it's describing. Yeah, so that's the exercise we're doing. So this is still far from modeling inflation. We're just learning. These are the baby steps to understand what's going on. Yeah, but there will be an important lesson, of course, waiting at the end. Yeah, thank you. Any more questions? Okay, let's continue then. Okay, so let me. Okay, I want to do the following. I want to grab this and put it here and make it more explicit. Yeah. Here I need to read what I want to write. Yes, this will look a bit messy, and perhaps you often don't see this in textbooks. But here I need it for inflation later on. I'll just do the following. I'll just replace these mode functions here. And let me tell you in advance what I will do. I will reshuffle things. Yeah, I will move some things to one side, move the other things to the other side. But that requires, in some terms, it requires making a change of variable of k and placing k to minus k. Yeah, I'm just telling you in advance what is going on. And the result of doing that, I leave to you to get to this result. So I'll just want to get here fast. So the result of doing this this game, actually I don't have it here in my notes. It is in the notes, but I don't have it in my handwritten notes. And I want to do it right. And I don't find it. Okay, I know where it is. Yeah, here it is. Okay, so the result will be the following. By the way, I missed something here, which I think I probably did write last lecture. These are integration constants, but I purposely will put this 1 over the square root of 2 omega. Yeah, did I put that last time? If I didn't, that was my mistake. It should be there. Sorry, it is in the notes. In such a way that this is really true. Otherwise, this is not true if I did not put this correct normalization factor. Yeah, it's just put in there because I knew that this was going to be the result. It doesn't make any difference. Okay, sorry about that. Okay, so this is why this is there. Okay, and now look what will happen. We will have AK B daga K plus or minus, sorry, BK B daga of minus K. So you can notice here that this comes from this procedure I told you before, that you have to make a change of variables from K to minus K. So this is one of the terms that is subject to that change. So this will now become e to the plus I K dot W. I will tell you soon what is that. And then here we have, I don't have too much space, so I'll go for another term, which is like that. And then this is just alpha K star B daga just of K minus BK star B daga of minus k. You will have that. I close here, and then minus EIK dot omega. So that's what we have. And this combination here is a Lorentz invariant combination, by the way. This is just, let me tell you that what's going on there is this is k times omega, which is, you have to read in the following way. This is minus, sorry, my mistake again. My mistake, there it is. So this is going to be minus omega t plus k dot x. That's what you get, yeah? That's one thing. Anything else I need to tell you? No, that's the expression, yeah? So now this is cool because this looks a bit more Lorentz invariant, yeah? Because we're dealing with a Lorentz invariant theory, because you all know that this is a Lorentz invariant combination, okay? So we managed to put together the Lorentz invariant form of the field. But what might not look as usual are these guys. Yeah? When you study QFT in a standard textbook, you see a different expression here. Yeah? In fact, I can tell you that I will rename these combinations, these two combinations. I will rename the one that is here as A, K daga, hat, sorry. And this one I will rename it as A daga of K. Yeah? And so this, what happens with this is that these new objects, these new operators, are also creation annihilation operators. Yeah? In fact, they do satisfy, they satisfy exactly the same algebra. Yeah? So they're genuine creation and annihilation operators. Yeah? So please look at them. Perhaps I should make it more explicit that how they do it look. I will just write one of them. Okay, this is the form, just for you to see it in more explicit terms. But this is the redefinition. We were working with B creation and annihilation operators, creation and annihilation, and now we got one which is called A. And my statement is that this combination, as long as this is true, this is important. If this is not true, then they will not be genuine creation and annihilation operators. But given that this is true, then it so happened that these are also creation and annihilation operators. Okay, that's the statement. You can check it. I will not prove it. It's a simple. This, by the way, is what is called a Bogolyubov transformation. Yeah. It moves you from one set of creation annihilation operators to another set of creation annihilation operators. Yeah? So by doing that, let me just clean up this expression. All of this is in the notes, by the way. So I clean up too much, perhaps. So this will become. Oh, no, it's fine, it's fine. These guys were not present. Yes, tell me. Yeah. Exactly. I just relabel, if you want. I did a Bogolyubov transformation, and so I left behind the B operators, and now I have these A operators. Yeah, and so let me just write them down. How do they appear in the end? So here you have, this was plus or minus plus, right? Sorry, I'm making the same mistake again. There you have, and then plus. I will just write the Hermitic conjugate just for simplicity. So we have that, yeah? And this is the expression that you always find in textbooks, right? Open up Peskin and Schroeder, and this is, you get it there immediately. I wanted to make this detour because both set of fields actually do quantize the system. Yeah, they're both equally true quantum fields. Yeah, one of them get creation annihilation operators multiplying plane waves. you see, and Lorentz invariant plane waves. The other one is just a bit more complicated, contrived. Well, I deleted it, yeah? And so you had waves, you have combination of waves propagating forward and backwards, right? So this is what is called the positive frequency solution when you quantize the field. It has a name, yeah? So why all the trouble? Why did we do that? Well, we now need to go to the next step, which is to analyze the spectrum of the theory. What does it mean? I need to know what's going on with the Hamiltonian. Let's write the Hamiltonian, yeah? So the Hamiltonian, let's go here. Oh, let's just go here. So the Hamiltonian, you might remember, is just the following integrals, 1/2 of pi. I'll skip many details here. And in this case, we had the potential before, but now that we're looking at the quadratic potential, it takes that form. So now you grab that expression over there, you plug it in, because these are all operators, right? You integrate. This is also a good exercise for you. And then some work there to be done, and then you get the following expression. You get a term, we'll call it H infinity, for obvious reasons. This is just a constant, and it's there, plus, and this is what you get, integration over k, omega k, times a dot daga k, a hat k. This is what you finally get. That's the result, after just grabbing that expression and plugging it back there. Question to you. What would have happened if I did not replace that version, but I did replace the version with B? What do you think it will have happened? Will we have obtained exactly the same expression, just with B's instead of A's? That sounds dubious, right? Because A's and B's appear in very different ways. Yeah? Will anybody bet what happened there? In fact, not. You get terms. You get a term like this. That's fine. But you also get terms which, for example, have two B's, not with daga, but just two B's, and two B dagas. So BB and B daga. Yeah? Okay? I'll come back to the meaning of that in a moment. But this is what we get from there. I'm just stressing that if you made the replacement with the B version, it's the same field. We never change the field. We just relabel things. Yeah? But you will have obtained a different looking Hamiltonian. It's the same Hamiltonian, it just looks different, that's all. Yeah? There's no difference, no different physics, after all. Yeah? Okay. What's great about that Hamiltonian? The part I haven't mentioned yet is that these creation and annihilation operators furnish a basis to construct states. This is called the Fock space, yeah? Which can be interpreted as a space filled with particles. Yeah? So this is just like the harmonic oscillator that you learn in quantum mechanics, right? There are ladder operators, and so you require some state which is the lowest energy state, yeah? And then you can create, for example, one particle state acting on this lowest energy state, which we will call the vacuum. Yeah? So this guy is the vacuum, by definition is the vacuum. And we define it in such a way that when an annihilation operator acts on the vacuum, it just destroys the vacuum, it becomes zero. Yeah? So this is just requiring that there is no lower energy states below the vacuum. So the vacuum is the lowest energy state. That's a requirement. Otherwise, we cannot construct anything. Yeah? So after that, after this, you have something which satisfies that. You can construct particle states. Yeah? So for example, one particle state which describe a particle with a given momentum, k, will be just proportional to a creation operator acting on the vacuum. I'm not taking care here of the correct normalization factor that will normalize these to. Those are just details that will not matter too much for this discussion. And then we can, for example, create a two-particle state, K1, K2, by just allowing two of these creation operators with distinguished momenta acting on the vacuum, and so on and so forth. You can construct as many states as you want. Yeah. In this case, we are obtaining, not because we demanded it, but just because we're dealing with a scalar field, we're obtaining bosons. These are they satisfy the bosonic statistics. Yeah? Okay. Now that we have, I have elaborated on the construction of this space, of the space of vectors, we can ask what's going on with the Hamiltonian. And it so happened that the Hamiltonian acting on any of these guys, for example, I'll make you an example with K1, K2. Yeah? So for example, what will you discover if you allow the Hamiltonian acting on a state representing two particles, yeah, of momenta K1, K2? Then you will obtain that this is equal to, well, first of all, this funny term, which is just a number, yeah? And then plus, you will get omega 1 plus omega 2. And I don't have space. I will just make it. Okay, and this will be, you will recover K1, K2. So these are eigenstates of the Hamiltonian, and that's what we gain. Okay, so these particle states, these states which we are labeling particle states, are eigenstates of the Hamiltonian, okay, with the correct energy content. So these are just these are the energies, the individual energies of free particles in the system. Then I will not comment anything on this guy. It's infinite. Yeah, the vacuum energy. Well, we just relabel the H, and I hide it there. We only measure differences of energy, so I'm not very worried about this guy. You add gravity. We don't know how to deal with it. Well, open problem. Okay. Good. Any questions so far? Sorry? Yes, please. Yes. So I leave to you to figure out what is H infinity. Okay? It's an integral of something, and it is obviously divergent. Yeah? It's just an infinite quantity. Yeah? Figure it out. Yeah? So you might wonder, well, should we be worried about this infinity? Yeah? And the answer is not really, at least not in flat space, because when we make measurements, for example, in colliders, we measure differences of energy. Yeah? It's not very different from just classical mechanics. In classical mechanics, if all the states have a common constant in their energy, you never measure that constant. So that's the statement. That we cannot really measure this quantity. Yeah. Yeah.
There is a way to start that term, right? By relating.
No. Okay. Good. That already happened because the original expression for H. Thanks for the question. The original expression had a term which is like this plus a term which goes like this. Yeah. So what I did is to use the algebra of creation annihilation operators. I'll just call it ladder operator for short, to interchange them, put them together, and that's how I got this. But the side effect of that is to get an infinite here. Yeah. This is what is called normal ordering. Yeah. Whenever you can make normal ordering, do it. Yeah. Grab your whatever operator you have, normal order it in advance, and that will save you time for later. Yeah? And so this is a byproduct of normal ordering. And then the question is, well, should we worry that it's an infinite quantity? Yeah? I'll just be cynical, say, no, not at all. Yeah? At least that's true in flat space, that we should not be worried. Then, of course, it is connected to cosmology because it's a contribution to the cosmological constant. But I will not get into that part. Okay? Okay? Yeah. Okay. Good. Let me just make a quick comment. Let me go back to these B operators. Yeah. So we know you know the difference between B's and A. And I want you to notice something. This is relevant for cosmology. Notice the following. Let me write another ansatz. Let me just write another ansatz for another solution. Let me call it phi B instead of phi that we have there. So to make it explicit, let me just call this guy phi A to remember that phi A has that form. Originally, it depends on B. Yeah? But now let me write a new ansatz for quantizing the system, which I will call phi B. Yeah? And my ansatz, you will realize immediately, is going to be the following. Just copying what I have at the right-hand side. No, I'll just write it like this. There you have. This is the. So what can you comment about this guy, phi B? Well, I can tell you that if I grab this, I examine whether it satisfies the quantum computation relations. Of course, it does. It does. It has the same property as this, so it's a genuine quantum field too. Yeah. However, if I grab this, so what I'm saying is that we could have done this from the beginning. Yeah. Set beta equal to 0, and this is what we'll have obtained. Yeah. And then we go back to the Hamiltonian. We throw it in the Hamiltonian, and what we will have obtained is that the Hamiltonian is h infinity plus k with omega, right? B daga B. That's what we will have obtained. Yeah. And that's a different spectrum. Why? Because A and B are different things. Yeah. So what I'm saying is that if this was our starting point, we reach the same results. It's just that with B's instead of A. Yeah. But these are different states. This is the point. Yeah. Remember that vacuum was chosen according to A. So let me call it the A vacuum. Yeah. And this means that there also exists a B vacuum around. Yeah. So there is some vacuum, which I can label the B vacuum, defined in such a way that B acting on that vacuum is just 0. Yeah. So now we're troubled because we have two different vacua. We have to choose between them. And when I say two different vacua, you immediately must understand that these are infinite choices because I can keep constructing more and more vacua because these are all obtained through Bogoliubov transformations from one to another. And there are infinite Bogoliubov transformations because of alpha and beta. There's an infinite set of alpha and beta that allows you to move in this space. Yeah? So what do we do now? I mean, which one is the correct vacuum to choose? Any answers? Well, the answer is, it doesn't matter. We have to choose one. Yeah? So let's just choose one. And I will stick to this one, to the A vacuum, just because I like letter A to be the label of creation and annihilation operators. But remember, there is also some B vacuum around, which is obtained from the A vacuum out of a Bogoliubov transformation. Yeah? Okay? And so this guy, what happens if you act on this other vacuum, which is not the A vacuum? What happens if you act, for example, with an A operator on this vacuum, which is not the A vacuum? What do you think it will happen? It will not get destroyed, first thing first. Yeah? In fact, you can show, and this is in the notes, you can show that the V vacuum consists of a collection of creation operators acting on the A vacuum. Yeah? Sorry. I will not do it here. And so there is an operator acting on the A vacuum that gives you the B vacuum. This is called the squeeze operator. So it's just a construction. But this is just to tell you that one vacuum, with respect to another one, is full of particles. Yeah? So what seems to be empty from one perspective is completely full of particles in another perspective. Yeah? This is relevant in curved spacetimes. Yeah? Because in curved spacetimes, you never get this really. Yeah? You never get a diagonal Hamiltonian. You can only diagonalize it at a given time. But after that time, you choose a time surface where you diagonalize it. Then you let time pass. And then it immediately becomes non-diagonal. Yeah? This is only true in Minkowski. Yeah? It's a sad fact that we have to deal with this. Yeah? So inflation is not a Minkowski. It's more like the Sitter. And it so happened in the Sitter, you cannot diagonalize the Hamiltonian everywhere. You have to choose a given time surface where to diagonalize it. And after that, it becomes non-diagonal. And you can understand that process as a Bogolov transformation. So now you have a sort of an evolution which consists in a Bogolov transformation. So what was empty, if your state was empty, now it starts to fill up with particles. Yeah? I'm just saying in words something which is you need to work hard to understand it, which is that in curved spacetimes, as opposed to Minkowski, which is completely flat, you have particle creation just because of the curvature of spacetime. Yeah? Yeah. Precisely, yeah. That's some people label it as gravitational creation of particles. Exactly, yeah. Yeah. I will not go into those details, but I wanted to mention it because it's an important fact, and so this allows us to understand, in fact, why do inflation? I will get that later to the details. Why in inflation we put as an initial state the vacuum state? Yeah, we postulate that the universe started empty. Yeah. Why is that a good postulate? Well, because inflation is very efficient at emptying the universe. So it dilutes whatever it was before. So you're left with just emptiness. Yeah? But nevertheless, because we're dealing with a curved spacetime, you still have creation of particles in a... Well, that's an interpretation, by the way. So you still have a creation of particles. And that's what explains, in a certain way, the fact that we observe fluctuations at the end of inflation, that you're left with a spectrum of fluctuations. These are fluctuations. The universe was empty, but nevertheless, you generated vacuum fluctuations, if you want. The fluctuation, well, you can keep calling them vacuum fluctuations, but if you want, you can also have this perspective where you created a state which is full of particles after you let evolve inflation for a while. Yeah, please. Well, here we're doing just Minkowski spacetime. Yeah? In curved space, that will not be true anymore. Yeah. I'm saying a lot of things that I haven't proved, but but you can check actually that this is very specific to Minkowski. Yeah? This is not true in any other spacetime, because of a very specific reason. Is because well, I want to leave it to you actually to get this and see why it becomes diagonal. It's because what was going to be non-diagonal, in fact, it is zero, just because we're dealing with Minkowski plane waves. Yeah? So I would prefer that you get your hands dirty for understanding this point. Yeah? It's a good exercise. Yeah. Exactly. That S is a unitary. Yeah. Yeah. Yes, you could, but the particle content is different according to one definition or the other. So one vacuum is empty of the particle that you decided that is empty. Exactly. Yes, precisely. Yes.
You're saying that A and B create different particles.
Exactly. That they define different vacua and particles. Yeah. You could say so. I never call them phi particles, but you could call them phi particles. Yeah. Yes, fair enough. Yeah. You could say same particles, just that, yes, no, I will not dispute that. It's just the states. We're talking about the states here, about what is the state of the system. Yeah. So one state of the system under one definition, under one definition for creation and initial operators. is empty according to that definition, but full of the other particles. The spectrum, in the end, if you want to qualify the nature of the particle, I think you will discover that they're exactly the same particles. They are labeled by the same labels in the end. Yeah, they're both bosons, zero spin. All of those labels will be the same. Yeah, yeah.
Sorry, I didn't understand why you said that. So we take the vacuum as the lowest energy state.
Exactly.
So why are you saying that there is particles in that state?
B particles. Yeah, yeah. So we defined we defined this vacuum here. At the beginning, I never put this label here, but once I got to that point, I had to go back, and I needed to put this label just to emphasize that this definition of vacuum is only for this set of creation annihilation operators. But you get an infinite set of creation annihilation operators through Bogolov transformations. Yeah, so you can get other vacuum in the end. Yeah. Hmm? Yes. Sorry. Yeah. Yeah. Well, nature will choose one vacuum for sure, and you can now spend, you can start doing philosophy about this and what is the fundamental vacuum. No, they're all equivalent. Yeah. For inflation, it's a bit different because we need to put initial conditions, and then we need to choose a vacuum. And what I was commenting is that you can have a perspective where the evolution is also consists of a Bogolov transformation a long time. Yeah. Yeah. Good. Let me move on because I don't want to get trapped in this discussion for too long. Good. I went through all of this. Yeah. So I want to very quickly now come back to the Lagrangian. I will write Lagrangians in this part of the blackboard. And now, just to prepare you for the future, well, Lagrangian or actions, doesn't matter. Just to prepare you for the future, I will now distinguish between space and time. I will break Lorentz invariance, yeah, or Poincaré symmetry, as you wish. And I will do it in this way. Not the only way to do it, but just because we need to learn something. I start with that term. I have done nothing. That term was already there at the beginning. Let me now start adding things that will break Lorentz invariance. I think you will all agree that, that this term breaks Lorentz invariance. I introduce what is called a sound speed parameter, and just by having it different from 1, different from the speed of light, you all understand that it breaks Lorentz invariance, right? It chooses a particular frame with respect which there is sound waves which propagate at that speed, yeah? When for very long wavelengths, yeah? For very short wavelengths. Then I will add another term. So if I'm not happy with breaking Lorentz invariance that way, I can make it even worse now. Because I will add that term, yeah? So I'm being malicious here because I'm pretty sure you could all quantize this, but now that I added this, I'm pretty sure nobody can quantize that, unless I tell you what is this function m, but I will not even bother. It's just some arbitrary function m, yeah? I will not even bother of stating that it has to be positive. I don't care. It's just a time-dependent function, yeah? You choose it. We can still say quite a lot about these systems, in fact, because, for example, the momentum out of this, you just work out what is the definition of the momentum, and you will find that the canonical momentum is just phi dot. Yeah, continues to be the same relation. That's because I did nothing to this part. Yeah, so nothing new there. So that's good because the momentum will play the same role as before. But everything else really spoils things. If you compute the equations of motions, for example, you will obtain the following equation. You will get that. It's a linear equation, at least something good out of it. There's linear. But I don't know how to solve it, so I'll just leave it like that. And then what else can I say? I can write immediately the Hamiltonian. I will not write the Hamiltonian because it will just be a waste of time. You can do it. Yeah, what can we do out of this? Well, there's quite a lot, because this still preserves some symmetries. Can you identify symmetries in this Lagrangian? We lost, of course, Lorentz invariance. That's a shame. But do we have any surviving symmetries? Excuse me? Translations, yes. And what else? Rotation. So we have Euclid symmetries. Yeah? This is a satisfied Euclidean group. Yeah? That's great, because that means, and Roman emphasized this before, we can do quite a lot, because there's still some symmetries left. And so we can still, well, nothing can stop us from still promoting things to field operators, because all the arguments I gave yesterday are still valid, yeah, about quantizing the system. Yes, please? No. If I say that, I take it back. I did not use the right wording. I just said I don't know how to solve this equation. But I want to show you that I can still quantize it. I can still get to some point. Yeah, I will quantize it. Yeah. It's just I won't be able to quantize it completely unless I don't know what is m. But I will leave that for inflation. Where in inflation we will encounter a very similar Lagrangian where I will know what is m, and then I will throw all the artilleries to this. Yeah, please. No, very fortunately not. Yeah, that will have happened if I put something which depends on time here. Yeah, but I did not. And this is free from that aspect. Yeah, so I didn't want to put everything yet in this. So I want to give baby steps in this direction. Yeah, thank you. Okay, so let me write an answer. And as I was saying, we can still do quite a lot. And one thing I will do is to write the answers for the field operator as a Fourier expansion of something. Yeah. So that will introduce also creation and annihilation operators again. So we can write this as k, and then some mode functions just as before. So I'm not doing anything new yet. I could write some B operators. Should I just write B or A? You know it doesn't matter now, right? I will write A, okay? In the notes, I think you have B, and I have another discussion about the Bogolov transformation. I will not make it here. And then we can write this term. So nothing new. Okay, so we have this expression. I think it really is the same as before, except for the fact that here you don't have the Lorentz invariant combination. This is k vector times x vector, right? Because t is still there in the mode function. Yeah, I need to find the mode function. The mode function will satisfy the following equation. There you have. That's the equation satisfied by the mode function. Yeah. And now, well, you can also compute pi, which I will not write, but pi is trivially obtained by taking a time derivative of this. So just do it, please. Take a time derivative of this, write pi. And next, let's impose the quantum condition. That means let's impose that these two guys, phi and pi, satisfy the basic quantum relations, phi pi equal to delta, phi equal to 0, pi equal to 0, commutators. Yeah, let's do that. And I will not do it. You will do it. And what you will find out of that, so you just grab everything. I'm leaving the equation of motion there. I'm not touching it. What you will find is that after imposing commutators, whatever is 0 or delta, depending on what you're computing, you will find the following condition. you will find that phi, you will find let me tell you in advance, you will find a condition on, not on A, because A satisfies the algebra you already know. So now we're not reinventing the wheel here. We just know that these are creation and annihilation operators. Let's forget about that. So the same relations. But now we get a condition on phi k, on the mode function. Yeah? And so the mode function needs to satisfy the following condition. There you have. This is what it is requested from the mode function. If or if. I mean, you need this to happen if you want this to, these are equivalent. Yeah? By assuming that creation and annihilation operators satisfy the Fock algebra of creation, of the one that we discussed. Do you think this actually can be imposed, really? Is it possible? We don't know what's the form of M. M is an arbitrary function of time. Well, it so happened that you can show it. This is an exercise. Yeah, if you're not familiar with it, you can show that this is always possible to impose on this. Yeah, or vice versa. Any solution of this can be tuned to satisfy that. Yeah. So let me tell you very quickly the story. You solve this, you will get a solution with two integration constants. I don't know what are the solutions because I need to know what is M. But I do know, because you all went to your course of differential equations, you all know that this has two integration constants. Yeah? And so I can tune them now. And then you can show that this is always possible. By tuning the integration constant, this is always possible. Yeah? This is called the Wronskian condition, because maybe some of you have identified that this combination here is related to the Wronskian transformation or Wronskian matrix. It depends on how you talk about it. And so you can always set the constants, the integration constants for this to be true. Yeah? So it's a nice exercise. I leave it to you. And notice that these quantities here play no role whatsoever. Yeah? Now, if that might seem a surprise, it should not surprise you at all, because yesterday, basically I gave you a proof that for any Lagrangian, and that means any equation of motion, you can always satisfy the accommodation relation. It is ensured. There's no way out of it. Why? Because Hamilton's equations are equations related to an algebra, yeah? And these satisfy that algebra, yeah? So this satisfied Hamilton's equations for sure. You just write the equations of motion for pi and phi. And so this is an outcome of Hamilton's equations, but you know that Hamilton's equations are consistent with this choice of accommodation relations. So this was ensured. This cannot be a surprise. Yeah? But it's just, you just work it out and you will see, this is the condition on the integration constant that you need. Yeah? So this in fact is equivalent to, if I go back to Minkowski, just for you not to be too lost about what I'm saying, this is equivalent to this condition. If you didn't see explicitly the form of the integration constants for the Minkowski case, these two things are the same thing. So go back to the Minkowski case, plug in those mode functions, and you will see that they're the same thing. Okay? It's just that here we have a completely arbitrary time-dependent background. Please. Yes. The Minkowski was, sorry, what was the question? When did we? Yeah, we lived here. We broke the Lorentz symmetries, yeah? No. This is condensed matter, if you want, yeah? This is a typical Lagrangian for condensed matter physicists. You just break, you keep the symmetries you're interested in, and so this has what is called Euclidean symmetries, yeah. But it's a good always that whenever you are generalizing something, just for sanity check, always go back to the simple examples that you know well, and this is what I'm doing here. I'm just reminding you what was the case in Minkowski. Good. Um, what else can I say about time-dependent backgrounds? I think that's the most important thing I want to say. Yeah, there's another thing that you can do on any type of backgrounds, which is, now I want to say something about non-linearities. So I'm getting ready for the last lecture on Friday. This is a quadratic action, therefore the equation of motion is linear. Yeah. Let's now make things even worse. I mean, this already is bad because it breaks Lorentz invariance, which we all cherish. But let's add more nonlinear terms. Yeah. Well, they're all linear there. They're all quadratic. They all give rise to linear terms in the equation of motions. Let's, for example, add. I never have space. Okay, I'll do it here, very small. So starting from n equals 3, you can guess that n will be the power of the field. Up to infinity, let me add here lambda n, phi to the n, over n factorial. For example, this is just any choice. Yeah, it doesn't matter. You can add other more crazy things. I don't care. Yeah. In fact, lambda could be, if you want, could be time-dependent, the lambda n coefficients. Yeah? What I will say now is something valid for any Lagrangian, even if you break more symmetries, it will be true. This is just for some context. So how do you deal with such a situation? Well, you can derive the equations of motion from here, and now you will find that this has more terms, which will look, I guess it will look like that. I hope I'm not mistaken. Okay, you'll have something like that equal to 0. Is this correct? Okay, you will have that, and then you need to solve it. Yeah. Well, remember last lecture. It doesn't matter how crazy your Lagrangian is or your action is. The Hamiltonian will make sure to evolve this. Yeah. And so the solution, whatever it is, the solution to this. In fact, don't forget this. I'm going back to the first 5 minutes of my last lecture, or well, after the overview. Yeah? That any observable in the Heisenberg picture, never forget this, can be written as the following. The following expression. Yeah? And this will satisfy that equation of motion. Yeah? This is easy to say because U is a complicated quantity. I mean, I need to know now what is U. It's the unitary evolution operator. So I say nothing really because solving this with that, okay, we're still far away from. But let's say you compute the Hamiltonian out of that. And what you know for sure is something I also wrote last time, is that the time derivative of this operator U is equal to H, no, in the opposite. It should be equal to that. Yeah. Remember this equation? I wrote it down. Yeah. Because we're in the Heisenberg picture, we can compute the time evolution of this, and well, so you tie the pieces. So this is what we got. Okay. Now, we're now dealing with a very complicated situation because we have all of these terms, which are very complicated, really. Yeah. But we can still, at least formally, get somewhere, which will be very useful to do. Let me do the following. Let me split the Hamiltonian in this way. Yeah? the splitting is up to you. Yeah? You decide what is H naught and what is you will call H interaction. In the present context, it's pretty obvious. It's kind of guided because I will call H naught the part which is quadratic, and H interaction the part that comes from the nonlinear term. Yeah. So you can say, okay, the action you can write it as some quadratic action which I called S naught plus S interaction. And then S naught leads to H naught, and S interaction leads to H interaction. That's how you can proceed. This is an art, because you have to decide how you will perform the splitting. It is not always true that it's good to leave all the nonlinear terms here. Sometimes it's good to move things from here to there, and so on and so forth, right? So you need to master that art. But for now, let me just take the plain view that H naught is the quadratic part and H interaction is the cubic part. Yeah? It depends on what you're examining. And let me now define U naught, which will be the evolution operator associated to H naught. Yeah? So it evolves the system as if it was a linear system. Yeah? What we're doing here is what is called perturbation theory. Yeah? We're just dividing something. This is not a cosmological perturbation theory yet, because we're dealing with just quantum fields. Yeah? But you can still grab the perturbations and treat them perturbatively. So this is what we're doing. We're not dealing with backgrounds here. We're just dealing with the perturbations. So we're saying, okay, some perturbations, well, linear perturbations are evolving according to H naught, and the nonlinearities are going to be in charge of H interaction. And now let me define U naught as the evolution operator which evolves the linear part of the theory, if you want. It's a way to say it. Yeah? So this guy will be, I will demand that it satisfies the following equation. That's how it is defined. Yeah? And what you know about this part of the theory, I don't need to develop it again, is that it evolves the linear equation of motion. The solution of the field of that part is just everything without this term. Yeah? So by doing that, we will find what is called the interaction picture field. Yeah? This will be very important later on. Yeah? Which is defined as the evolution of guided by U naught acting on phi of x t0. So that's the field, the full field evaluated at t naught at the initial time. Yeah? But it's evolved according to H naught, not the full H. Yeah? So you will have that expression. Okay? Any questions? I hope you're all following the logic. Yeah, so we're dividing the theory into two sectors. One is trivial because we know how to solve it. Yeah, it's the simple thing that we did before. So this guy, I can actually now, okay, this is a question just to check that at least a few of you are following me. Oh, thank you. Yeah, but that was not my question. What is the equation of motion followed by this interaction picture field? What do you think is the equation of motion that it follows? The hint here is that it evolves as a linear field. So it satisfies the linear equation of satisfies this equation of motion. Yeah? Of course, if I'm not specifying what is M, I don't know how to solve it. Yeah, but it's still linear equations of motions are trivial in many senses. So we can say a lot about them just because they're linear. Yeah, as we did before. Yeah. Okay, so this sector is completely taken charge of. I don't need to say anything else about that. The important thing I want you to remember is that this object, phi I, the interaction picture field, satisfies that equation. Yeah? That's the only thing I need you to keep in mind. And now, I'm really sorry I made a mistake. First I wrote it okay, and later I modified it. So please swap it. I'm sorry about that, and here too. Yeah? You have to swap them. Please correct them. Yeah. Yeah. Oh, I will now. I will now. Yeah, I will now. I deal with the easy part. Yeah. 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 Not yet. Not yet. Okay. So now I will define the following. I will define after this. We'll define a new operator, a new evolution operator, which I called UI. Which is defined as U naught daga of T naught times U of T naught. Yeah. Let me check that this is correct. Yeah. Okay, this is a new definition. There's a lot of definitions here, I know. This guy is the full evolution operator. This one is the one we just discussed. Yeah. And what you can show, these are just statements here, and these are exercises. You can show that the full field, taking everything into account, all the nonlinearities, has the following form. But this is obvious. This is really this is not an exercise, just because it follows very easily. So that's one statement, okay? The other statement that you can make, well, the other thing that you can discover is that if you compute a time derivative of UI, you will discover that this is equal, let me remember the right order of H. You will discover that this is equal to this, where HI, which is not H interaction, HI is defined as, well, it has an obvious definition, but let me just be careful here. Is defined as U naught of T naught acting on H interaction of U naught of T naught. This is what you will find, okay? Okay. This expression has appeared 3 times already in different formats, right? But this is the one I really care about. Yeah. The others were just formal, and I will work with this one. Yeah. And then there is an exercise for you. Half of the exercise is explained in the notes, but I don't have time to work it out here. As Roman say, life is tough, and I need to use that advice here. You can show that the solution to this equation, so we're searching UI. Everything else we know. Yeah, we know HI. The only thing missing is to know UI. Yeah? And there is a beautiful solution, which is the following. Which is given by that. That over there, if you plug it back in that expression, it satisfies that expression, okay? You will have to accept it for now, yeah, as a true statement. I need to clarify, though, what are a few objects present in this expression, and how to read it. Do you know what's the name of this formula? The Dyson formula, yes. I mean, this means something, which is not very explicit, but first of all, we need to make sense of that exponential. What is that exponential of a time integral of those operators? Yeah. Well, here you have an operator, first of all. So what it means to exponentiate an operator, what it means to exponentiate a matrix, well, all of this is just symbolic. It means that this is really a series which start from n equal to 0 to infinity of 1 over n factorial. So you just take the series, the Taylor series for the exponential, and that allows you how to read this expression, which will be minus I to the n. And then be careful here, because you might be tempted to grab this and just expand it in powers. But the way to read this is that this is a sequence of integrals of dt1, dt2, so on and so forth, yeah? And then here you have a sequence of these operators evaluated at t1, t2, so on and so forth, and up to the last one, yeah, which is n. Yeah? That's the way to read it. Yeah? So now you see, oh yes, these are really operators acting in sequence, yeah, one after the other. What about this? Do you know this quantity here? It's a symbol. It is called the time ordering symbol. It is required. It is an instruction. It tells you that whenever you have a sequence of time-dependent operators, yeah, under this symbol, you're free to order them in such a way that, well, you're not free, you're instructed to order them in such a way that the operator that has the lowest time, you move it to the right. And then the second operator with the lowest time, you move it next to the first one, and so on and so forth. You have to order them in time. Yeah? So this is a mess. It's a mess because you have integrals, which goes from t0 to t, so you have all the possible orders, but this symbol is telling you, well, in whatever stage you are of integrating these things, you have to make sure that always the lowest time operator appears at the most right place possible in this sequence. Yeah? Yes? You will not like my answer. It's part of the exercise. Yes. Okay, you go to that expression and you integrate it once. Let me do the first step for you. You integrate it once here. And then you get something else here. You get ui minus ui evaluated at t0, let's say. This is 1. Yeah? Well, the matrix of value, the operator of value 1. Yeah? The identity operator, sorry. And now you move this to the right. So you have this solution. Yeah? That's the first stage. And now you have to iterate this. Because here you have something evaluated at t, but here you have something evaluated at t prime, because you're integrated in t. Yeah? And now you start iterating. You start plugging back this equation, iterate. You do it an infinite time, and you will get that sequence. That's the answer. Yeah? And by doing that, you will realize when you iterate, you will realize that you're always putting the lowest time at the right. It's ordered naturally by the iteration process. Yes? Exactly, exactly, yes. That's why the T appear here is just to order all these nested integrals, yeah? It's really ugly. And it's the source of all the headaches in primordial cosmology. Because whenever we have to compute correlation functions, we're dealing with nested integrals, which are a real pain in the body. Yeah? And when you want to compute loop corrections, much of the difficulties of loop corrections come from this fact. Yeah, it's just a comment. Okay. Last thing I want to say, I don't have too much time. This is up to 15? Okay, yeah. No, I think I have enough time, yeah. So to wrap up this discussion, the full field, just for you to see it in full glory, the full field looks like this. Let me write it first. This is very symbolic, of course. This is the full expression for the field. Very formal. You will not make anything out of it yet. Yeah? And then let me move on to statistics of quantum fields. So this is the outcome I wanted to discuss in this part of the discussion. There's a last bit of discussion which I will make in 15 minutes. Yeah? 15 minutes, please. Okay. In cosmology, and well, I think Roman was already very eloquent about this. I won't say it better than it was said this morning. There are very privileged objects which are called endpoint correlation functions. And I will focus on what are called equal time endpoint correlation functions. I think Roman was also talking about them. Because you can compute correlation functions even at different times. Yeah? For example, I want to correlate a field at time 1 with another field evaluated at different space and time. That can be done. But I will focus on correlation functions at equal times. Yeah? So they are just defined in the context of these lectures, as opposed to Roman's lectures. In these lectures, since we're doing quantum mechanics, we will just define them in terms of the state of the system. So there you have the state of the system, which is time independent. Remember that. Doesn't depend on time. All the time dependence is in the operators. And this is the expression that you want to compute. Okay, so these are endpoint correlation functions. Where what do? You grab this and plug it there. So it's becoming more and more difficult. Yeah? So let me first discuss the computation of endpoint correlation functions not for the full field, but let me neglect the interaction term. Remember, this was interaction, sorry. Let me say there is no interaction. We're dealing only with the linear theory, with the quadratic action. Yeah? Okay? So in this first stage, and let me do something else. Let me be interested in the particular case where the state of the system is the vacuum. I'm not obliged to do that. You can study computation of endpoint correlation functions for systems full of particles. For example, a bath, a thermal bath. That can be done. In this case, I will focus on how do the statistics of quantum fields look when the state corresponds to the vacuum. And I will call those, well, not me, but everybody calls them vacuum fluctuations. Yeah? These are just, we will compute the expectation values of the field fluctuating when the state represents nothing, represents a system devoid of particles. Yeah? So So in this, I did two simplifications, right? So the object we are discussing now, after these two simplifications, is the following. That's the object, okay? Remember, this is a very contextual statement. We're not computing endpoint correlation functions under any circumstances. We are looking for correlation functions for a state which is devoid of particles, and when the field corresponds to the linear field. So I'm not looking at nonlinearities, okay? And now this is a trivial problem to do, and this is an exercise too in the notes. Yeah, what you will find. Well, let me make first a question to you. What happens if I have only one field? Can you say immediately what happens? It is zero. Who say that? Well, many people. And could you quickly say what's good? But I'm going for an operational answer. Like, what's the operation that will make you find that this is zero? Let me complement the answer. This you can expand in terms of creation and annihilation operators, as we know. And the annihilation operators immediately destructs the vacuum. What happened with the creation operator? The creation operator is acting on the other vacuum because it's the same relation, it's just the conjugate. And so this is zero altogether. So there's nothing going on. What happens if we have three fields? Not two, three. Not one, three. Same thing, operationally. You will discover that because we have three creation operators in any order, the fact that this is an odd number of creation annihilation operators always kills either the right vacuum or the left vacuum. There's no way out. Yeah? Okay? So just operationally, you will discover that this is zero for any n being odd. Yeah? What happens if we have an even number of operators? Well, you will discover the following, that this is equal to a product of, I will first define them like that. Then plus permutations. I haven't told you yet what is delta. I'll tell you immediately. Delta is, let me define it. There are time dependencies, but I'm not a delta. You will find that is equal to what I will call the power spectrum, which depends on time. Yeah, so finally I'm making a connection with Roman's lectures today. And the power spectrum is just the mode function square, that is the power spectrum. Yeah? This is what you will find. Well, let's say that what you will find if you do this computation, you will find first a previous stage. I should have said that first. But this is equal to is equal to that, yeah? Okay, and then you prove that. So you first get to this, and then you go to that, okay? That's not difficult to find. So let's focus on what's going on here. So this is for n even. And do you find this familiar? I don't remember exactly if Roman did show the same result. Yeah? This is a Gaussian statistic. This is precisely the Gaussian statistic. You can ask how many of these guys are there. And you will find that this is a number of n equal n factorial over n over 2 factorial, 2 to the n divided by 2. That's the number of possible combinations of pairwise combinations of these guys. Yeah? These are sometimes called propagators in some context. They're pretty much Feynman propagators, basically. But I'm focusing here on the statistics. This is just to tell you that the statistics of vacuum fluctuations, when we're talking about nonlinear, where nonlinear terms are absent, respect a Gaussian statistic. Okay? That's a very important thing. So that connects with, and it starts to show you some impressions of why inflation predicts a Gaussian statistics. We haven't proved it yet, but it's just giving you some hints. So to finish, I still have, yeah, please. Exactly, because, well, for sure one can make a connection, but this is the vacuum state. So I'm just asking, what is the expectation value of the field, which is an observable, when the state is devoid of particles? Yeah? It's perhaps not intuitive because you don't have particles, but you still have fluctuations. Fluctuations of what? Well, the vacuum state. Well, you're already familiar with the harmonic oscillator, right? And you know that the lowest state of the harmonic oscillator still is something that that does something in a sense, right? Which happens to be the mode function happens to be a Gaussian, by the way. Yeah. So here we are basically. This is a version of that. Yeah. So you might ask, well, why is it Gaussian? Well, the wave function of the lowest energy state of the harmonic oscillator, which is described with a quadratic action, is Gaussian. This is basically the same answer. Yeah? So you already know that the wave function of the lowest energy state of the harmonic oscillator is a Gaussian. This should not be so surprising. We're basically making a very similar statement. Yeah? So in my last minute, I'll just say the last thing. I hope you give me 1 minute. But I'm still within the time. Okay. We assume that this was the vacuum. Okay, I will stick with that because computing the statistics of states which are not devoid of particles is a bit harder. I will not do that. But I will now address the question of what happened if we turn on interactions. Remember, this was for interaction picture field. That means the linear field. What happened if now this guy is present? Now turn it on. There are no linearities now. Well, things become pretty tough because I need to plug this, replace it here. Yeah, this is the vacuum. But under certain circumstances, I can give at least one more step. The circumstance is the following: is when this is weak. The interaction is very small. There is a parameter which I can make it next to zero. There's some epsilon parameter, yeah? And it will be literally epsilon, the slow roll parameter, which comes in the following lecture. So if that's true, if this is small, we can actually expand the exponential. So do it, please do it. Expand the exponential, and you will find that that the statistic, the endpoint correlation functions, has a Gaussian part, which I will call just G over there, which you already know is the one described there. That's the Gaussian statistics, plus something. That something modifies the Gaussian statistic. This is called a non-Gaussianity. Yeah? And this expression, this has the following expression, is a minus I. This comes from expanding that. Remember, expanding the exponential to first order in the interaction. So it will have the following form. Sorry. I'm finishing here, don't worry. The vacuum state at the left. And then you have a commutator between two things. In the left, I will put phi I. These are the simple objects. Well, there is time, remember that. There's a product then of these guys. There you have. well, time is important here. They're all evaluated at t, yeah? Not t prime. T prime is being integrated. These guys are evaluated at t, comma, and now I put the interaction picture Hamiltonian, which is evaluated at t prime. I close it, and then I close the sandwich with the other vacuum, the other state. This is the result, yeah? These are the disconnected contributions to the endpoint functions. And this, well, you need to compute it, but at first order in the interaction, it leads to connected pieces, yeah? So going back to Roman's discussion, here there is a systematic, you need to work it out, there is a systematic way of working connected contributions to endpoint functions, and the disconnected one are the Gaussian part, so now you have to deal with this. This can also give rise to disconnected part, but normally you want to go for the connected ones, yeah? So by working out this, and these are my last comments, you can actually reconstruct what are called Feynman diagrams by just doing weak contractions, which means seeing how different pairs of creation and annihilation operators start to annihilate each other with the algebra, yeah? So you can work it out that this is, well, this is done for particle physics, for example, in Peskin and Schroeder in a very conventional way, and Feynman diagrams follow from here. But you can also do it for cosmology. For primordial cosmology, you can always work Feynman diagrams in any perturbative context. But this one in particular is it gives you a scheme to compute endpoint functions. Yeah. So I'll leave it to this point. I want you to keep this equation written in a special place in your notes, because we will come back to it in the last lecture. Yeah, not tomorrow, not on Thursday, but on Friday. I want to use this to compute what are called non-Gaussian contributions to the endpoint functions. For example, the bispectrum, the primordial bispectrum, which is an important observable, which we haven't yet managed to observe because actually inflation basically predicts it to be basically zero. Yeah, so we will see that prediction, and we will see hopes of predicting something different from zero, actually. Yeah. Thank you very much for today.
So more questions for Gonzalo? Yes, just a sec.
Yeah, so thanks for the lecture. The definition of the deltas are the integral of the power spectrum. So isn't this the correlation function? Or am I wrong?
Yes, precisely. This is a correlation function in coordinate space, in configuration space. You can work it out in momentum space if you want. That will be the power spectrum in a sense. This one here is the definition I deleted. I'm sorry. But it's just a two-point function in coordinate space. Okay. So it's basically, yeah, I told you you can also call it the Feynman propagator in the context of particle physics, but this is, we're computing here things at equal time. Yeah? So it just happened to be the correlation function, the two-point correlation function in coordinate space. Okay. So you can see that it's the same statement as Roman was saying, is that a general n-point correlation function can be expressed in the Gaussian statistic case, can be expressed as a collection of two-point functions. Yeah, so it's the same statement, but this is a result of just computing vacuum expectation values of interaction picture fields. Yeah, so it's an outcome, if you want, of a very minimal assumptions. It's a very Just a comment, it's very interesting because Roman is forced, because of what he's studying, he's forced to introduce the concept of random fields. Yeah? I am free of that. I am just working with quantum fields, and so I do this computation. But the justification in the end, the ultimate justifications of considering random fields in cosmology, if you want, comes from this setup, if you want. Why did acquire such a statistics? Well, because underlying of all the explanation, there were quantum fields. So far, I haven't said how is this done in cosmology. I haven't done cosmology yet, yeah? But we'll get to that point very soon.
Thanks for the lecture, Professor. So, in particle physics, one usually uses Feynman diagrams to compute scattering amplitudes. So we have particles at a given time, and we are interested in particles in another time. So in cosmology, we usually compute correlation functions for the same time, as we were telling. So would the Feynman diagrams change in this situation, and if so, what would they become?
Yeah, good. Thanks for the question, because there are many similarities with the usual stuff that you see in a conventional textbook of quantum field theory oriented for particle physics. Yeah? But there is a departure at some point. In particle physics, you're interested in computing amplitudes. That's correct. But there is an intermediate stage, which is to compute endpoint correlation functions in particle physics. But there, you're not interested in the same endpoint correlation function we're computing here. There, you're interested in, how to say this, in time order endpoint correlation functions. That means, in particle physics, you will consider this type of object, but you will put the T symbol here. You will order them in time. Why do you do that in particle physics? It's because there is a formula, a very famous formula known as the LSZ formula, yeah? Which connects those type of correlation functions, the time order correlation functions, with amplitudes. Yeah, there is without that formula, you cannot do anything in particle physics. Yeah, it's a very important formula. Here, we are taking a different perspective. For us, the observable is the field. Yeah, so we're assuming that we can measure this field in cosmology. Yeah, and for that there will be well, other experts, not me, here in this room. And next week you will keep hearing how to do that. Yeah, how to extract, how to observe those fields. Yeah, how to observe these endpoint correlation functions. Yeah, and here we're interested in endpoint correlation functions. Yeah. Now, let me just complement the answer, is that here you have let's say, an evolution in one sense, and then an anti-evolution. By the way, I didn't mention what was this. I hope it was obvious that putting a bar over T is an anti-time ordering. You have to order things in the inverse as the time ordering symbol dictates. Yeah? So actually, the Feynman rules for these type of objects are very different from the Feynman rules of particle physics. Because now, well, I don't want to enter into the details, but now you have this evolution going into the future and then going to the back. That doesn't happen in particle physics, because in particle physics, you're always evolving from the in state to the out state. Here is a different story. And therefore, Feynman rules, which exist here, they take a different form where you have a multiplicity of degrees of freedoms. You have more degrees of freedoms than you have a... So if you have a particle propagating as a virtual state in particle physics, here you have 2 copies of those particles. Yeah? It's just one minor change. But otherwise, it's basically the same formalism. I would say here it's a bit more complicated, but...
Thanks for the answer.
Yeah, thank you.
Any more questions? So you can save the questions also for the
Of course.
free Q&A session after lunch. So let's thank Gonzalo again for this very nice talk.